And I want to be right from the beginning, just a reminder that all of these problems are Newton's second law problems. And I didn't make that particularly clear Friday, so I want to make sure I kind of, make it very clear today that an object traveling in a circular path has to have an unbalanced force. So the first problem we're going to do, a lot of people try to, balance the forces, but there is no balance to these forces. It's purposeful this way. So we're going to do the Gravitron problem, or the spinny ride problem. It's a pretty common question. I don't think you'd ever see it on an AP exam, because I think it's actually not going to be the kind of question they would ask on an AP exam. But we're talking about the kind of problem where a person is on one of these rides where they are going to appear to, stick to the back of the ride. So, not sure if I'm giving you the name right. The way they usually call it at amusement parks would be like the Gravitron, but there's 2 or 3 different versions of this ride. There's the kind of the ride where you are just in a dark room, and it's got like indoor-outdoor carpeting on the walls, and you spin against the wall, and they drop the floor out from underneath you. There's also the one where it's all open, and they take the whole thing and kind of tilt it upwards on its side. And then there's the version of it where you're spinning, and the whole thing is like a big pendulum, and you're mounted like that, and they spin this thing backwards and forwards. You guys seen any of these at the amusement park? So we're going to focus on the simple part of it, meaning we're going to look at the part where we're just doing the spinning part, and you are feeling as though you are stuck against the walls. Now, let's be really clear. You are not being flung against the walls in the manner in which you think, or at least some people think. Some people think that they are just actually being thrown outwards. That is actually not true. They are moving in a straight line, this straight line. That is the direction of their velocity at any instant on the ride. And that will be the direction they will travel unless the ride prevents them from doing so. Remember, your inertia will make you go in a straight line unless acted on by an unbalanced force. Now, I think we can all agree this is not the direction you wish to be going for any sustained amount of time. You would prefer to stay a part of the ride, which means you would like to be going this way after a short time. And you still don't want to continue along this blue line. You would really like your body to be moved in such a way that you are now over here and now traveling this way. In all of these particular examples, you are traveling tangent at every instant. And the only way your velocity is changed is if there's an unbalanced force that is pushing on you to change your direction. That unbalanced force would have to be towards the center. So some net force acts on you this way. Now, what I would like you to consider is, what is the minimum speed necessary for you to successfully participate in this ride? Let's assume that you have a mass of m. Let's assume a coefficient of static friction of mu s, and that the ride itself has a radius, capital R. This is a pretty typical kind of question for this. It's actually, if it shows up, this would be like multiple choice. They would not expect this problem to take you very long. For us, this is a kind of an introductory question. So it's the first one we're actually going to kind of work through to see how we're going to use UCM in problems. We're going to do a couple like this today. So we'll start with this one. And let's also start by kind of considering how we would draw a free body diagram. And I don't want to be overly critical here, but you do need to kind of figure out in these problems, where you are and where the unbalanced force is, so that you can kind of create a image of, well, what is the state of the problem? Meaning, looking at this top down, I might miss some of the forces. This system is clearly three-dimensional in nature. So you need to find a vantage point at which you can kind of identify the forces in your problem. For the most part, our problems are still going to be able to be two-dimensional. And so seldom will we see a three-dimensional problem where you have to express the forces in 3 dimensions. This one, I would probably wait till the person's on their side like this, so that we're seeing kind of a side view of them, and then consider the forces that are acting on them. From this vantage point, I hope you all realize that we're still going to have kind of our standard set of forces acting on them. They've got to experience weight. They're in contact with the wall, so the wall has to apply a normal force. And if they don't slide down the wall, they've got to be experiencing an upward force. What is likely causing the upward force? I think we're probably talking about friction. I'll point out that I made the normal force the largest force in the group. That should make some sense. Friction has to be equivalent to the weight, so I need more normal force than I have weight, because friction is likely to be less than the normal force. So when you're experiencing this ride, and for those of you, how many of you have ridden one of these? So you do feel like not only are you laying on your back, but that you are heavier. You have to feel that way because you're experiencing more normal force than you normally have when you're laying down. Now, the net force here is not equal to 0. You all right there? Are you good to go? Yeah. Okay. The net force isn't equal to 0. In these problems, the net force has to be equal to ma. It has to be an unbalanced force. Now, I think we can all agree that the net force in the y direction might be equal to 0. We would like the friction to be balanced by the weight. But the net force in the x direction, definitely ma. And for us, this problem, that's mac. It's got to be the centripetal acceleration that we're talking about here. Now, this problem is not particularly hard, and we've done one kind of like it, the ones where we were talking about the book being held up against the wall. So I think that we can kind of skip some of this. We know that it's friction minus the weight that has to be equal to 0. And it's the normal force that has to be equal to mac. Now, once we recognize that this is a uniform circular motion problem, that means our acceleration isn't about changing our speed, but is about changing our direction, which means we have an immediate replacement of acceleration with v squared over r. Be prepared to do that. That's almost always a point on the AP exam, recognizing when you're going to be substituting v squared over r for the acceleration. Now, this part we've done. We've done this kind of stuff a lot. The only change is here. But this next part is the part that we tend to have some difficulty with. And so I want to remind you that this is a threshold problem. You're interested in finding out the minimum velocity necessary for you to stay stuck against the wall. So there's got to be some threshold struck here. And hopefully, when you see that you're dealing with static friction, that helps identify that you're going to be dealing with the inequality portion of friction. That's where your threshold's going to come from. We have different kinds of threshold questions. Some of them you have to set some number equal to 0 or some value equal to 0. Some of them are going to work in an inequality. Be prepared to know which is which. This one, we have an inequality. And because it's an inequality, we sub into the inequality. So I'm going to say that friction is equal to mg. That's less than or equal to us times mv squared over r. Just doing all of my substitution. Now, when you build these rides, you want to build them in such a way that they are accessible to as many people as possible. So it's not accidental that these rides are designed in such a way where the size of the person shouldn't play a role in their enjoyment of the ride. Generally, if a person's not allowed on a ride and it's because of their size, it's usually because they're too small, not too big. And it's usually because the safety equipment can't hold them in place should there be a problem. So for the most part, when we deal with size, you're dealing with kids, little kids. They're not tall enough for the safety equipment to hold them in place. And rides are designed in this way. There are very few rides that need your mass in order to be successful in operating. And I'd be very wary of those kinds of rides. Now, you're supposed to figure out the velocity here. And I don't have any problem with you guys, doing the math here. I'm sure you guys are very aware of what you have to do here. And you're looking for a minimum velocity, so it should work out in such a way that you get something that indicates a minimum. This is telling you that the velocity has to be greater than or equal to this. This is the minimum value. And yes, I can square it both sides, but I want to wait for just a minute. Let's make sure this makes sense. First, if the surface is stickier, the bottom number gets bigger. That tells me that if it's a stickier surface, I don't have to spin it as fast. Does that make sense? Stickier, right, doesn't require as much normal force. That's good. Also, bigger radius means I don't have to spin it as fast. Now, generally, the size of these rides is not determined by how fast they want to spin them. Usually, the size of these rides is based on how big they are to fit on the back of a truck, because these are almost always carnival rides or usually they're state fair or carnival rides. You're not going to see this at Disney World or Busch Gardens or something like that. Although they had one of these at Busch Gardens. The one at Busch Gardens was exceptionally small. That's why they got rid of it. It made people sick. So, although, have you ever ridden like the teacups or one of those spinny kind of rides? They keep those radiuses pretty small. Don't whip your head back because you'll never get it back, forwards. Have you ever done that accidentally when you were little? Put your head back and look upwards. That'll make you sick. Always keep your head forward. Now, here's the problem for most of us. They would never accept the answer here in meters per second. They're not going to want that. And I mean this in a very straightforward way. The whole ride is spinning. So far this year, when we've talked about velocities, we've talked about an object moving through space. But when we talk about something that is spinning, there's other ways to measure velocity. This problem, although gives us a linear velocity, you should probably be aware that we would probably want something called an angular velocity. And if you've never heard of angular velocity before, today's your day. Because talking about this as a linear velocity wouldn't make a whole lot of sense since the ride's not going anywhere. A person on a ride might have a linear speed, but the ride itself is staying in place. It's spinning. So generally, we wouldn't ask for the minimum speed of a rider. We would probably ask for the minimum angular speed of the ride. Angular speeds are measured in things like rotations or radians per second or minute. That's generally the speed that we would use. If we ever use radians in here, it will never be for sine, cosine, or tangent. When we use radians, we use it for angular measurements. And usually for velocities, we don't use radians anyways. For velocity, we usually use rotations. So if I was asking about this ride, I'd probably ask how many rotations per minute it makes or how many rotations per second it makes. That's a more useful value for us. But that doesn't change the fact that this relationship gave us the linear velocity and not the angular velocity. Now, just be honest with me. How many of you guys know how to go from an angular velocity to a linear velocity? It's a pretty small handful. So we probably should have that conversation real quick. So if you've never done this conversion before, it's no big deal, but you need to know this conversion. For just a moment, G is meters per second squared, R is meters, and mu has no units. So the unit of our answer was meters squared per second squared. And since we hadn't taken the square root yet, that's an appropriate set of units. This is always the best way to figure out whether you're getting your answer correct or not, is take a look at the units of the values that are there. We have the linear value, but if you want to know how fast the ride should spin, then we can substitute omega times the radius squared and use that to get the angular speed. This would be the angular minimum speed of the ride. Okay. It just depends on what your problem asks for. So you need to be prepared. We'll practice a little bit. But now you know a little bit about the... So let's just talk about this for just a short, brief moment. We will be reiterating this, and you'll be dealing with it a lot second semester, since second semester is all about angular motion. But when it comes to uniform circular motion, this topic comes up pretty frequently, so I think we kind of need it now. What we just found with our centripetal acceleration was the linear speed of the guy while he's on the ride. That's what this is. It's a linear speed. It's in meters per second. In fact, if we look back at angular speeds are in radians or rotations. It really depends on what your problem asks you for. But we use a different symbol for angular speed. For angular speed, we use the Greek letter lowercase omega as opposed to a v. So almost all of the angular measurements are in Greek letters. You already know one, we use angular displacement. I've never used the word displacement with it, but theta is just an angular displacement. So we've already used that one. So we use the lowercase omega, which is just a fancy W. And it's lowercase, so when you consider what that looks like, here's our kindergarten letter stack thing. So omega would be like that. At least that's how I write it. So when you're looking at your work or you're wondering what it is, that's what it's going to look like. In typed print, it looks very similar to that. It'll look italicized though. So be prepared to see that, especially as we get closer to second semester. We start doing more angular motion. You already have an equation that converts this. You just don't know it yet. It's the definition of circumference. Circumference is a relationship between an angle and a radius. But what it also is linear equals angular times radius. It's how you convert any measurement from a linear measurement to an angular measurement. Circumference is the same formula. It's the linear measurement, how far around a circle you go. 2 pi is the angular measurement for a circle, and r represents the radius. So you've always been walking around with the conversion, because almost all of you know how to calculate circumference. So if you want to calculate or convert a linear measurement to an angular measurement, v will equal 2 pi, v will equal omega times r. The linear value equals the angular value times the radius. That's how you convert from a linear value to an angular value. Now, this part, incredibly important. This value, when you use it in a problem, will always be in radians per time. Always. So if you actually calculated this and you solve for omega, then what you would find is that it's in radians. So if you were asked to find rotations per minute, you would have to multiply or divide by 2 pi to go from radians to rotations, or the other direction, if you're going from rotations to radians. I assume that part you know, but I don't like to make assumptions. So if you're in radians per second and you need rotations per second, then you'll need a multiplier that's going to convert this. And you have to remember that for every 1 rotation, there are 2 pi radians. So in going from radians to rotations, you divide by 2 pi, that gets you rotations. If you're going from rotations to radians, you multiply by 2 pi. Rotations should be a smaller number than radians. Now, we're just doing our work symbolically, so we don't have to worry about units. But I do want to be clear that we could rewrite centripetal acceleration in terms of the angular measurement. And sometimes that's a much better way to think. For something that is spinning, it's probably appropriate to use the angular version of centripetal acceleration and not the linear version. This is the ladybug on the record problem, the coin on the record problem. Generally, they want to know how fast the record spins. That's not a linear speed, it's an angular speed. So, going between the two. All right? How about another example? And this is just one to see if this is acclimating at all. Let's consider, this is a classic question, and it's the one that we talked about just a minute ago, the coin on a record. If there's a coefficient of static friction between the coin and the record, what maximum speed can you spin the record without the coin falling off? Coin and record problem. Let's say that the coin is located a distance r away from the record center, and let's say the coin has a mass of m, and you'd like to find out what the maximum speed is. Would you all agree that if you go too fast, the coin will slip off? Does that make reasonable sense to you guys? Because if it's not moving at all, it's probably not going to slip off. Only if it's moving is it going to slip off. So probably the faster it goes, the more likely it'll slip. So before we start this problem, you need to find the right vantage point in order to draw a free body diagram that makes the most sense. So I'll let you try that out. Because if I just give it to you, it's too easy. So what would be the right vantage point? Draw a free body diagram for the coin and consider what the right vantage point would be to do so. So I'm going to put the coin on the edge. Center is like right there of the record. So I'm looking down its edge. That, to me, is the right vantage point because from here, I recognize there's got to be a frictional force this way towards the center in order for the coin to stay on the record. Looks like friction is providing the centripetal acceleration. Still going to be mg downwards. Normal force upwards. I have my unbalanced force, and it is that unbalanced force that's going to cause that coin to travel in a circular path. It's telling them they have to go to their classroom. We're probably going to get interrupted to tell us that don't release anybody to lunch yet. Maybe not. Now, I don't really think I have to do the rest of this problem for you, but I'm really trying to drive home the fact that I'm expecting a lot out of you guys. Net force equals MA. Coin's actually the thing we're looking at, and it's traveling in a circular path. So I'm going to go ahead and put the X in here and remind us that that's going to be in the X direction. And the only force in the X direction is friction. So friction equals M. Now you can either go V squared over R or omega squared times R. I'm going to put omega squared times R. I think it makes more sense to get the angular speed of the record and not the linear speed of the coin. Sometimes it will not be obvious which thing you're supposed to get, but it says what maximum speed can you spin the record. So I'm thinking angular speed of the record is probably more valuable here. And folks, if you don't know the difference about what I'm talking about, put in your notes that you should stop and consider whether you should use linear speed or angular speed. This is your first time coming through here and you think it'll just be obvious. It won't be. Or I wouldn't bring it up in class. Now, the other side of this is just the net force in the y direction. I know I'm going to need this because it's got friction. And our friction problems are always going to bring together normal force. Now, it's still a threshold problem. So, friction less than equal mu times the normal force. I'm going to sub into my inequality. So, m omega squared r less than or equal to, I'm doing that sub here, mu naught mg. Cancel the m's. We're looking for the speed, so I'm just going to divide both sides by r and get that omega squared has to be less than or equal to USG over R. Now, there's some important things here that you should think about. Because if I were asking follow-up questions, I got some. Like, does it make sense that mu is in the numerator? Would a stickier surface allow you to go faster on the record? Looks like it's in the numerator, so I'd get a higher speeds. But I'm also going to look at the fact that R is in the denominator. So if I make R bigger, you make R bigger, it's easier for the coin to fall off. So you guys have to go.